This is problem 3 on practice exam 1 of chapter 2 in the book Problem Solving with Differential and Integral Calculus. We have a rule of thumb, the 70-50 rule. You should be at least 70% of the takeoff speed when you're halfway down the runway, a rule that airline pilots use. This trajectory qualifies because the speed looks like at about 310 feet per second. Typical takeoff speed is 250 feet per second. So we're going to use this speed versus position down the runway to do some calculus. Part A asks, at 2,000 feet, estimate the slope, and then from the slope, calculate how the change in speed of the plane from 1950 feet down the runway to 2050 feet down the runway. Part B asked for the same thing at 8,000 feet. Part C asked us to get the slope from the normal equation. Let's start with part A. 2,000 feet down the runway is right here. Let's put a point there. Let's draw a good tangent line. We need to get the rise over the run. To help us get the run, let's draw a vertical line here. The rise looks like it goes from about 90 to 600. That's 510 feet per second. The run, that's 10.4, that's 10.8, that's 11.2, that's 11.6. It's about halfway between 11.6, so that's 11.4. The slope is about 0.0447 feet per second every foot. And I really shouldn't put 3 significant digits here, but let's do it. Maybe we'll get a point or 2 off. When the plane travels from 1950 to 2050 down the runway, it's a little distance from here to here. It travels 1,000 feet, and that's going to be our delta x. And we're going to use the slope to get the delta y. So there's the slope. The change in the vertical is delta v, and delta x is 1,000 feet. We can solve this for delta v. It's about 4.47 feet per second. So when the plane is at 1950, and then it goes to 2050, the change in speed is about 4.47, 4.5 feet per second. On to part B. Well, first let's zoom in. Let's zoom in to that curve around 2,000 feet to see if the speed increased by that much. So that's 1950, that's 2050, that's 2,000. We're using the slope at 2,000 to extrapolate. At 1950, it looks like it's 176.6, a little bit above that feet per second. At 2050, it's a little bit above 181.1, something like that, feet per second. So this actual line is curved. That's not the tangent line. We're just zooming in on the line, and it looks straight. We're using the slope at 2,000, and we're extrapolating out. So we hope we're close. So all we can say is we're not wrong. 176.6 to 181, that's very close. That changes 4.4 something. So on to part B now. Now we're going to do 8,000. First, we label the point, and then we draw a good tangent line carefully. And to get what this is, we're going to have to draw a horizontal line over the axis. Okay, so the rise, that's like 180 to 178. This is 440, and that's 460. It's a little bit less than half, 448. And the run is the whole thing. That's easy. The run's 12,000 feet. So the rise about 270, and again, 3 significant digits is pushing it. That is delta v over delta x, the rise over the run, with our tangent line. So when the plane goes from 7950 to 8050, it goes 1,000 feet, and we can get the change in the vertical direction, delta v. And we plug in the numbers, and we get about 2.25. So it doesn't accelerate nearly as much with distance when you're at 8,000 because it's going so fast. So in 100 feet, the speed changes by 2.25 feet per second if you're at 8,000 feet. So let's do the same thing. We'll zoom in. This is around 8,000, so 7950 to 850. This line's actually pretty straight here. 356, a little bit of 366, maybe halfway. 356.5. I'm eyeballing it here. 358. 0.9. Okay. And you subtract them, you get 2.25. That's pretty good. On to part C. This is the equation of the line. We have to take the derivative of this. And then we're going to compare. Perhaps you know the rule for taking the derivative of x to the 1/2. But we're not going to rely on rules. We're going to figure it out for ourselves. First, we're going to square both sides. So we get v squared over here, and we eliminate the square root on the right-hand side. And we know what the derivative of v squared is. We've done enough. It's 2v dv. We've done this in chapter 1 and chapter 2, so we can just write it down. The right-hand side is straightforward. You have a constant times x. I want to know how much this changes when I change x by dx. And it's just simply 16 feet per second squared dx. So if it's not obvious, draw a graph, explore, figure it out, say, now I see how this works. That's the goal. We want you to understand how it works. So there's the derivative of both sides of the equation. And let's repeat it here. Now we want to get the slope, which is dv dx. So we divide both sides by dx, put the 2v in the bottom. If we want the slope, we really should get rid of the v. And we know what v is. It's right here. That's v. So we can stick this in for v. So this curly bracket here is just v. Now we have a 16 feet per second squared on the top and a square root in the bottom, so that makes a square root in the top. And the 2 is not under the square root. We're going to pull that out. But the x is under the square root. So we have 1/2 square root of 16 feet per second squared divided by x. That's the slope. Now we can plug in x and calculate the slope at any point, which is pretty powerful. We don't have to draw multiple tangent lines. We just plug in 2,000. If we plug in 2,000 right here, we get, oh my goodness, 0.447. 3 significant digits. That's complete luck. We eyeballed that tangent line and we got lucky. At 8,000 feet, we just plug in 8,000 to get the slope, and we get 0.0224. We estimated 0.0225, and we're ecstatic with how close we were. That's pretty good. That's problem 3.